Tonight, we're going to explore one of the most profound questions in human history. Not whether we'll get to Mars, but whether the first people to step foot on that red desert world will ever come home. You've probably heard countless stories about Mars missions, about colonizing the red planet, about humanity's future among the stars. But here's what most people don't realize. The first humans to reach Mars might not be going on an exploration mission. They might be going on a one-way trip. And by the end of tonight, you're going to understand exactly why bringing them back might be impossible, why they'd go anyway, and what it means for the future of human civilization. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Think about every exploration mission in human history, every expedition to unknown lands, every journey across uncharted oceans, every climb to the summit of an unconquered mountain. What did they all have in common? The explorers came home. Magellan's crew sailed around the world and returned to Spain in 1522. Edmund Hillary climbed Everest and descended back to base camp. The Apollo astronauts traveled to the moon and splashed down in the Pacific Ocean a week later. Every exploration, no matter how dangerous, no matter how far from home, included a return journey. That was part of the plan. You went out, you discovered something new, and you came back to tell the story. Mars might be different. Mars is not like the moon. The moon is close, cosmically speaking. It's about 384,400 kilometers away. That's 238,900 miles. The Apollo astronauts reached it in about 3 days. The entire trip, launched to splashdown, took about 8 to 12 days depending on the mission. They could see Earth from the moon's surface, hanging in the black sky like a blue and white marble. They were never more than a few days from home. If something went wrong, if an emergency happened, help was theoretically possible. The communication delay was only about 1.5 seconds. Ground control could talk to the astronauts in near real time, guiding them through problems, making decisions, coordinating responses. Mars is nothing like that. Mars is on average about 225 million kilometers from Earth. That's about 140 million miles. But that's just the average. Mars and Earth both orbit the Sun, and sometimes they're on the same side of the solar system, sometimes on opposite sides. At their closest approach, called opposition, Mars is about 55 million kilometers away. That's 34 million miles. At their farthest, when they're on opposite sides of the Sun, the distance stretches to about 400 million kilometers. That's 248 million miles. The distance constantly changes as both planets move in their orbits. This creates the first problem with a Mars mission: timing. You can't just launch whenever you want and expect to reach Mars. You need to wait for what's called a launch window, a period when Earth and Mars are positioned correctly relative to each other. These windows open roughly every 26 months. Miss the window, and you have to wait over 2 years for the next one. The journey itself takes between 6 and 9 months, depending on the trajectory you use. 6 to 9 months of traveling through empty space, confined in a spacecraft, breathing recycled air, eating stored food, unable to turn back. The astronauts will watch Earth shrink behind them until it becomes just another point of light. Communication with Earth will have a time delay that gets worse the farther they travel. At Mars' closest approach, radio signals take about 3 minutes to cross the distance. That means If an astronaut sends a message to Mission Control, it takes 3 minutes for that message to reach Earth. Then Mission Control's response takes another 3 minutes to come back. 6 minutes minimum for any exchange. When Mars is farther away, that delay stretches to over 20 minutes each way. Over 40 minutes for a back-and-forth conversation. This makes real-time communication impossible. You can't ask a question and get an immediate answer. You send a message, you wait, you receive a response, you wait again. Everything has to be done in bursts, like sending letters rather than having a phone call. And if something goes wrong during those 6 to 9 months of travel, the crew is on their own. Mission Control can offer advice, but by the time that advice arrives, the crisis might already be over, one way or another. Now, let's say they make it. Let's say the spacecraft survives the journey without any critical failures. Let's say the astronauts remain healthy, the life support systems keep working, the navigation is accurate. After 6 to 9 months of travel, they finally arrive at Mars. They fire their engines to slow down, they enter Mars orbit, they prepare for the most dangerous part of the entire mission: landing. Landing on Mars is extraordinarily difficult. The atmosphere is thick enough to create heat during descent, requiring heat shields, but too thin to slow the spacecraft down effectively with parachutes. Mars' atmosphere is only about 1% as dense as Earth's atmosphere. A parachute that would safely land a capsule on Earth barely does anything on Mars. You need retro rockets, you need precise timing, you need everything to work perfectly. If the parachute deploys too early or too late, if the retro rockets fire at the wrong altitude, if there's any malfunction in the landing sequence, the spacecraft crashes, and there's no second chance. You get one attempt. NASA calls it the 7 minutes of terror. That's how long it takes for a spacecraft to enter Mars' atmosphere and reach the surface. 7 minutes of automated systems making thousands of decisions because the radio delay means Mission Control can't help. By the time Mission Control sees the spacecraft entering the atmosphere, it's already been on the surface for several minutes, either intact or destroyed. The crew watches their instruments, follows procedures, and hopes everything works. They're passengers during those 7 minutes, trusting systems built and tested on Earth to function correctly on Mars. And let's say they succeed. The landing system works. The retro rockets fire at the right moment. The spacecraft touches down on the Martian surface. They're now standing on another planet. They're the first humans to set foot on Mars, experiencing something no one in history has ever done. They can see the rust-colored sky, the rocky desert stretching to the horizon, the distant mountains silhouetted against the sunset. It's an achievement that will be remembered for as long as human civilization exists. But they're stuck there. Here's why. Getting off Mars is almost as hard as getting to Mars in the first place. You need a rocket powerful enough to lift off from the Martian surface, accelerate to escape velocity, and begin the journey back to Earth. That rocket needs fuel. A lot of fuel. More fuel than you could possibly bring with you on the initial journey. The spacecraft that brought them to Mars is designed to land, not to take off again. It used most of its fuel during the landing, burning through propellant to slow down, to control the descent, to touch down gently. What's left isn't nearly enough to escape Mars' gravity. So you'd need a separate rocket. A Mars ascent vehicle, pre-positioned on the surface, fueled up and ready to go. But how do you get that rocket to Mars? You have to send it ahead of the crew, land it successfully, and ensure it's still functional when the astronauts arrive months or years later. You need to land a complex piece of machinery on another planet and have it sit there in the Martian environment, exposed to temperature swings from minus 125 degrees Celsius to plus 20 degrees Celsius, exposed to dust storms, to radiation, to the gradual degradation that happens to anything left outside in harsh conditions. And it needs to work perfectly when the crew finally needs it. But even that's not the hardest part. The hardest part is fuel. Rockets are mostly fueled by mass. The Saturn V that sent astronauts to the moon weighed about 2,800 metric tons fully fueled. That's 6.1 million pounds. Of that mass, about 2,600 metric tons was fuel. Only about 43 metric tons was the actual command and service module that went to the moon and back. The rocket was 93% fuel by weight. And that was just to reach the moon, which has 1/6 of Earth's gravity and no atmosphere. Mars has about 38% of Earth's gravity. That's stronger than the moon, but weaker than Earth. It also has that thin atmosphere which creates drag during ascent. Getting off Mars requires a substantial rocket, which means substantial fuel. If you wanted to launch a crew of 4 or 5 people, plus equipment from Mars' surface, and send them back to Earth, you'd need a rocket comparable in size to what SpaceX is developing for Earth launches. And that rocket would be almost entirely fuel. You can't bring that much fuel from Earth. The mass would be prohibitive. If you tried to land a fully fueled ascent vehicle on Mars, the landing spacecraft would be so heavy that you'd need even more fuel just to land it safely. It becomes a vicious cycle. More fuel makes the spacecraft heavier, which requires more fuel to land, which makes it even heavier, and so on. The numbers don't work. So the proposed solution is to make the fuel on Mars. Use Martian resources, primarily carbon dioxide from the atmosphere and water ice from the soil, to manufacture methane and oxygen propellant. This process is called in situ resource utilization. You send equipment to Mars that can extract carbon dioxide from the air, mine water ice from underground, electrolyze the water into hydrogen and oxygen, combine the hydrogen with carbon dioxide through the Sabatier reaction to produce methane and water, and store the methane and oxygen as rocket fuel. It's chemically possible. We know the reactions work. We've done them in laboratories on Earth. The chemistry is straightforward in principle. The Martian atmosphere is 95.3% carbon dioxide. You can compress it, purify it, and feed it into reactors. Water ice exists in the Martian soil at high latitudes and in permanently shadowed craters near the poles. You can mine it by heating the soil or drilling into ice deposits and extracting the sublimating water vapor. Once you have water, electrolysis splits it into hydrogen and oxygen. 2 molecules of water become 2 molecules of hydrogen and 1 molecule of oxygen. The hydrogen then combines with carbon dioxide in the Sabatier reaction, discovered by French chemist Paul Sabatier in 1897. 1 molecule of carbon dioxide plus 4 molecules of hydrogen yields 1 molecule of methane and 2 molecules of water. This reaction is exothermic, meaning it releases heat, which helps drive the process. The water produced can be recycled back through electrolysis to generate more hydrogen, creating a closed loop where you only need to keep adding carbon dioxide from the atmosphere. The methane and oxygen are then liquefied for storage. Liquid methane stays liquid at minus 161 degrees Celsius. Liquid oxygen at minus 183 degrees Celsius. Both are colder than the coldest natural temperatures on Mars, so you need active cooling systems with refrigeration units powered by electricity. The tanks must be insulated to minimize boil-off, the gradual evaporation of cryogenic propellants over time. Even with perfect insulation, some fuel will be lost. If you're producing propellant months or years before the crew arrives, a significant fraction could evaporate before it's ever used. But doing it on Mars is different from doing it in a controlled laboratory. You need power, lots of power, to run the extraction equipment, the electrolysis, the chemical reactors, the liquefaction systems that convert the gases into storable liquids. A fuel production plant capable of generating 30 to 50 metric tons of propellant over the course of 18 to 24 months might require 100 to 200 kilowatts of continuous electrical power. That's equivalent to the power consumption of about 70 to 140 average American homes. But there's no power grid on Mars. Solar panels are one option. Mars receives less sunlight than Earth because it's farther from the Sun. At Earth's distance, the Sun provides about 1,368 watts per square meter. At Mars' average distance, that drops to about 590 watts per square meter, less than half. And that's at local noon, on a clear day at the equator. Factor in the day-night cycle, seasonal variations, dust in the atmosphere, dust accumulating on the panels, and the angle of the sun, and your average power output is much lower. You might need several thousand square meters of solar panels to generate the necessary power, and they all need to be deployed, connected, maintained, and kept clean. Dust is a major problem on Mars. During dust storm season, which can last for months, the atmosphere can become so hazy that sunlight is reduced by 50 to 99%. Global dust storms occur roughly every 3 to 4 Martian years. When one happens, solar power drops dramatically. The Mars Exploration Rover Opportunity died during a dust storm in 2018 when its solar panels couldn't generate enough power to keep the batteries charged and the heaters running. The rover froze and never woke up. A fuel production plant relying entirely on solar power could face the same fate. Nuclear power is more reliable. A kilopower reactor, currently being developed by NASA, could provide 10 kilowatts of continuous power from a uranium fission reactor, about the size of a trash can. You'd need 10 to 20 of these for your fuel plant. Or you could use a larger reactor design capable of generating 100 kilowatts or more from a single unit. The Soviet Union operated nuclear reactors on remote Arctic bases for decades. The technology is proven. But launching nuclear material to Mars raises political and safety concerns. What happens if the launch fails? What if radioactive material is scattered across a launch site or falls back to Earth? These risks are manageable, but not trivial. And once on Mars, the reactor needs cooling. You can't use water cooling like Earth-based reactors because water is scarce and mostly frozen. You'd need radiative cooling with large heat radiators that dissipate heat to the Martian atmosphere and surrounding environment. More mass, more complexity, more things that can fail. You need automated systems that can run for months or years without human supervision because you have to send this equipment ahead of the crew and have it produce fuel before the astronauts even leave Earth. Everything must be robotically controlled. Sensors monitoring temperature, pressure, flow rates, composition, power levels, structural integrity. Control systems making thousands of decisions per day, adjusting valves, starting and stopping pumps, regulating reactor output, managing battery charge states. Maintenance robots capable of replacing failed components, clearing dust from solar panels, repairing broken connections. These systems need to work in a dusty, cold, radiation-soaked environment where maintenance is difficult and replacement parts are impossible to get. Mars temperatures swing wildly. Near the equator, daytime summer temperatures can reach 20 degrees Celsius, but they plummet to minus 73 degrees Celsius at night. At higher latitudes, or in winter, temperatures can drop to minus 125 degrees Celsius. Most materials become brittle at these temperatures. Seals crack, lubricants freeze, batteries lose capacity, electronic components behave unpredictably. Everything must be designed to survive thermal cycling across a range of 200 degrees Celsius or more, day after day, for years. Radiation is relentless. Cosmic rays and solar radiation bombard the surface continuously. Over time, radiation damages electronics, causing bit flips in computer memory, degradation of solar panel efficiency, embrittlement of plastics and composites. A fuel plant operating autonomously for 2 years before the crew arrives will accumulate significant radiation exposure. Shielding helps, but adds mass. Every kilogram of shielding is 1 less kilogram of fuel production equipment or scientific instruments or habitat supplies. Mission planners face constant trade-offs between protection and capability. And you need it to produce tons of fuel. Literal tons. A Mars ascent vehicle might need 30 to 50 metric tons of propellant to reach Mars orbit and begin the journey home. 50 metric tons is 50,000 kilograms, about 110,000 pounds. To put that in perspective, that's roughly the mass of 35 automobiles. All of it must be manufactured from Martian resources, using equipment sent from Earth, operating autonomously for months or years in one of the harshest environments in the solar system. The production rate depends on the size and efficiency of your equipment. A well-designed system might produce 100 to 200 kilograms of propellant per day. At that rate, generating 50 metric tons would take 9 to 18 months of continuous operation. If anything breaks down, if a pump fails, if a reactor goes offline, if a dust storm blocks the solar panels, production stops. The timeline extends. The crew's departure window starts approaching. Mission planners watch nervously from Earth as weeks turn into months, hoping the equipment restarts, hoping enough fuel is ready in time. If the production rate is too slow, the crew has to wait longer on Mars, consuming their life support supplies, exposing themselves to radiation, increasing the risk of equipment failures. Life support systems degrade over time. Air recyclers accumulate contaminants. Water purifiers clog with minerals. Spacesuits develop leaks. Everything wears out. Redundancy helps, but you can only bring so many spare parts. If the crew lands expecting to stay for 18 months and they end up staying 30 months because fuel production fell behind schedule, they're operating on margins that were never designed for that duration. Something will fail. Maybe it's not critical. Maybe it is. Maybe they can improvise a repair. Maybe they can't. If the production stops for any reason, if the reactor fails, if a dust storm covers the solar panels for too long, if any component breaks down, the crew has no way home. They're stuck on Mars indefinitely, waiting for the next cargo mission from Earth to arrive with replacement parts. Assuming Earth even has replacement parts ready to send, assuming the next cargo ship launches on schedule and lands successfully. It could be years before help arrives. The crew would have to survive on dwindling supplies, rationing food and water, stretching their resources as thin as possible. hoping they can last until resupply. This is the central problem. Getting to Mars is hard. Getting back is even harder. And the difficulty isn't just technical. It's logistical, economical, and practical, in ways that compound with every added requirement. Every system needs backups. Every backup needs monitoring. Every failure mode needs a contingency plan. The mission architecture becomes exponentially more complex with each new requirement, and complexity is the enemy of reliability. The more components you have, the more connections between them, the more failure points exist. And on Mars, failure can mean death. Engineers try to minimize failure modes through careful design. They test components in Mars simulation chambers, subjecting them to low temperatures, low pressures, abrasive dust, radiation exposure. They build redundancy into critical systems. 2 reactors instead of 1. Multiple pumps where 1 would suffice. Backup sensors, backup controllers, backup power supplies. They design for graceful degradation, where losing 1 component reduces capability but doesn't cause catastrophic failure. But testing on Earth only goes so far. You can simulate Martian conditions, but you can't perfectly replicate them. The dust on Mars is finer and more abrasive than any Earth dust. The atmospheric composition is different. The gravity is different. The radiation environment is more complex than what you can reproduce in a test chamber. Some things you can only learn by actually operating equipment on Mars. And by the time you learn those lessons, it might be too late for the first crew. This is why some mission planners have proposed a different approach. Send multiple fuel production units on separate cargo missions. If one fails, others can compensate. Land them in different locations to reduce the risk that a single dust storm or local environmental event affects them all. Start production years before the crew launches, giving plenty of time to identify and fix problems remotely. Build up a large stockpile of fuel, far more than the minimum required, so there's margin for losses, for inefficiencies, for unexpected problems. But every additional cargo mission costs hundreds of millions of dollars. Every extra fuel plant adds mass that must be launched from Earth and landed on Mars. The costs compound. A mission that might cost $50 billion, with 1 fuel plant could cost 70 or 80 billion, with 3 plants operating in parallel. And that money has to come from somewhere. From taxpayers, from government budgets, from resources that could be used for other purposes. The question becomes whether society is willing to pay that price for a round-trip mission when a one-way mission costs a fraction as much. Think about the Apollo program. The United States spent about $25.8 billion between 1960 and 1973 to land 12 people on the moon. That's about $280 billion in today's money, when adjusted for inflation. For 12 people, for 9 days total on the lunar surface, spread across 6 missions. For missions that lasted at most 12.5 days from launch to splashdown. The infrastructure required was enormous. Hundreds of thousands of people working for over a decade, developing new technologies, building massive rockets, training astronauts, setting up tracking stations around the world, all for brief visits to a world 3 days away. The scale of the Apollo program is difficult to comprehend from our modern perspective. At its peak in 1966, the program employed over 400,000 people directly and indirectly. NASA's budget consumed more than 4% of the entire federal budget, something unimaginable today when NASA receives less than half of 1%. The Saturn V rocket, still the most powerful rocket ever flown to completion, required entirely new manufacturing facilities. The Vehicle Assembly Building at Kennedy Space Center, where the Saturn V was assembled, remains one of the largest buildings by volume in the world. Tracking stations were built on islands across the Pacific and Atlantic Oceans to maintain communication during lunar missions. The computational, navigation, and medical challenges were immense. This was before modern computers or software engineering existed. Medical challenges were unknown territory, requiring new protocols for zero gravity while minimizing every gram of mass. Life support systems had to be essentially perfect. 12 astronauts, spending about 9 days total on the lunar surface, meant about 2,000 person-hours in the lunar module environment, plus another several thousand person-hours in the command module during transit. The air had to be scrubbed of carbon dioxide using lithium hydroxide canisters. Water had to be managed carefully because every drop was precious. Temperature had to be maintained in the harsh thermal environment, where sunlit surfaces reached 127 degrees Celsius and shadows dropped to minus 173 degrees Celsius. On Apollo 13, when an oxygen tank exploded, crippling the command module, the crew had to retreat to the lunar module designed to support 2 people for 2 days and make it work for 3 people for 4 days. They survived, barely, by improvising carbon dioxide scrubbers using duct tape and plastic bags, by shutting down nearly all systems to conserve power, by enduring near-freezing temperatures as the cabin cooled without heaters. The fact that they made it home is a testament to engineering, ingenuity, and sheer determination. And all of this massive effort, all of this expense, all of this risk was for missions to the moon, a world 3 days away. With no atmosphere to slow you down during landing, with 1/6 Earth's gravity making launch and landing easier, with communication delays measured in seconds, not minutes, with Earth always visible in the sky as a reminder of home. If you had a medical emergency on the moon, you could be back in Earth orbit within 3 days, back to a hospital within 4 days. That's tight, but survivable. If critical equipment failed, you could abort the mission and come home immediately. Apollo 13 proved that. A round-trip Mars mission would cost exponentially more. You'd need larger spacecraft for the longer journey, more supplies, more redundancy, more life support capacity. Instead of a 1-week mission, you're looking at 3 years. Instead of 3 astronauts in a capsule the size of a van, you need 6 to 8 astronauts in a habitat large enough to maintain psychological health over that duration. Instead of simple, stored consumables, you need regenerative life support that can recycle air and water for years. Instead of batteries and fuel cells for power, you need nuclear reactors or massive solar arrays. Instead of a single lunar module, you need descent vehicles, surface habitats, rovers, ascent vehicles, fuel production plants, and all the infrastructure to support them. The mass comparisons are staggering. The Apollo Command and Service Module combined weighed about 32 metric tons. A Mars transit vehicle would weigh several hundred metric tons fully loaded. The lunar module weighed about 15 metric tons. A Mars lander with habitat might weigh 100 metric tons or more. Everything scales up. More mass requires more fuel to launch from Earth. More fuel requires larger rockets. Larger rockets are more expensive to develop and build. The costs multiply at every stage, and you'd need the fuel production infrastructure on Mars, the ascent vehicle, the systems to keep everything running during the year and a half the crew would spend on Mars, waiting for the next launch window. Because you can't just leave whenever you want. Just like the trip to Mars requires the planets to be aligned correctly, the trip back requires waiting for Earth and Mars to be in the right positions again. If you land on Mars and the launch window back to Earth has just passed, you're stuck there for over 2 years, waiting for the next window. Earth and Mars align favorably for missions only every 26 months. If you arrive on Mars and just miss the optimal return window, you wait approximately 26 months for the next one. There's no way to speed this up. Orbital mechanics is unforgiving. 2 years on Mars. 730 days, minimum. That's how long the crew would need to survive in their habitat. Breathing recycled air, drinking recycled water, eating stored food, supplemented by whatever they can grow in Martian greenhouses. The psychological challenge of that duration cannot be overstated. You're confined to a few rooms, or, if you're lucky, a few connected habitats. You can go outside, but only in a spacesuit, which is hot, bulky, and limiting. You can't feel wind on your face. You can't smell flowers or rain. You can't take a walk in nature. Everything is filtered through technology. Research shows crews experience significant psychological stress after about 6 months in confined environments. Small habits become infuriating. Depression is common. Sleep patterns deteriorate. Cognitive performance declines. These effects build gradually until you're not functioning at full capacity. Physical health deteriorates as well. Mars' gravity is only 38% of Earth's. Your bones don't need to support as much weight. Your muscles don't work as hard. Even with rigorous exercise, bone density decreases and muscles atrophy. Astronauts on the International Space Station in zero gravity lose about 1 to 2% of their bone mass per month despite exercising 2 hours per day. On Mars, with some gravity, the loss would be slower but still significant. After 2 years, an astronaut might have lost 20 to 30% of their bone density, increasing fracture risk and potentially causing chronic pain. Medical issues are another constant worry. What happens if someone gets appendicitis? On Earth, that's a routine surgery, minor risk. On Mars, with no hospital, no surgical suite, no anesthesiologist, no blood bank, it becomes life-threatening. You could train one crew member as a doctor, equip them with surgical tools and medical supplies. But they're not a full surgical team. Complex surgeries require multiple people with specialized skills. A dentist, a radiologist, an anesthesiologist, a surgical nurse. You can't fit all those specialties into a crew of 6 to 8 people while also covering the engineering, piloting, geology, biology, chemistry, and other skills needed for the mission. Telemedicine helps. The doctor on Mars could video conference with specialists on Earth, getting guidance during a procedure. But remember the communication delay. 20 minutes round trip when Mars is far from Earth. You can't have someone talking you through each step of a surgery when their instructions arrive 10 minutes after you needed them. You'd have to operate based on pre-recorded training videos, detailed procedures written before the mission, and your own judgment in the moment. The doctor would be essentially alone, making decisions that could mean life or death for a crew member, with no immediate help available. Radiation exposure accumulates relentlessly during those 2 years on the surface. Cosmic rays penetrate the thin Martian atmosphere and bombard the surface continuously. A year on Mars exposes you to about 240 millisieverts of radiation, compared to about 3 millisieverts per year on Earth's surface. The increased cancer risk is significant, but not immediately fatal. It's a long-term effect that might not manifest for decades. But it's cumulative. Every day on Mars adds to your lifetime dose. Every hour outside in a spacesuit, where shielding is minimal, adds more. By the time the crew returns to Earth, if they return, they'll have absorbed radiation doses that NASA's current safety standards would never permit for any existing mission. These standards exist for good reason. Studies of atomic bomb survivors, radiation therapy patients, nuclear accident victims, and astronauts who've spent time in space show clear correlations between radiation exposure and cancer rates. The data is definitive. More radiation means higher cancer risk. For a Mars mission, mission planners would have to accept higher risks than any previous human spaceflight program has tolerated. They'd have to argue that the benefits of the mission outweigh the increased probability that crew members will develop cancer later in life. Some would argue that's a decision the crew members can make for themselves, accepting the risk knowingly. Others would say it's unethical to expose people to that much radiation regardless of their consent. All of this assumes everything goes reasonably well. No major equipment failures. No unexpected medical emergencies. No psychological breakdowns. No accidents during surface operations. But Murphy's Law applies on Mars just as it does on Earth. Anything that can go wrong eventually will go wrong, given enough time. And 2 years is a long time. The habitat could develop a leak. Micrometeorites, small particles traveling at extreme velocities, constantly bombard Mars. The atmosphere is too thin to burn them up like Earth's atmosphere does. A micrometeorite impact could puncture the habitat wall. If the hole is small, a few millimeters, the air loss might be slow enough to detect and patch before pressure drops dangerously. If it's larger, the habitat could depressurize in minutes. The crew would have to seal themselves in spacesuits, find the leak, patch it from outside if necessary, all while dealing with the panic and stress of a potentially fatal emergency. Or a critical system fails. The oxygen generator stops working. The water recycler clogs. The carbon dioxide scrubbers become saturated. Each of these is a countdown to death. Without oxygen, you have minutes. Without water, days. Without CO2 removal, hours to days, depending on how many people are breathing in, how much volume. Redundancy helps. You bring backup systems, spare parts, multiple ways to accomplish critical functions. But redundancy adds mass and cost. And even with redundancy, if 2 systems fail simultaneously, you're in trouble. The crew would need to be extraordinarily resourceful. They'd need to diagnose problems with limited diagnostic tools, repair equipment with whatever materials are available, jury-rig solutions when the proper parts aren't available. They'd need to think creatively, work together under pressure, and maintain their composure when lives are at stake. These are the same skills that saved the Apollo 13 crew. Improvisation, determination, and the ability to solve problems with limited resources. But Apollo 13 lasted less than a week. A Mars mission lasts years. The crew would need to maintain that level of performance day after day, month after month, for the entire duration. And throughout all of this, they're exposed to bone loss, muscle atrophy, radiation, isolation, confinement, and the constant awareness that help is at minimum 6 to 9 months away. If something goes catastrophically wrong, if the habitat is destroyed, if multiple crew members die, If a solar flare floods the area with lethal radiation, there's no rescue mission coming. Earth can send condolences, maybe launch a memorial mission years later to document what happened, but they can't save anyone. The crew is truly on their own, in a way no explorers in human history have ever been. After those 2 years, if everything has worked perfectly, if the fuel is ready, if the ascent vehicle is functional, they climb aboard, launch off the Martian surface, and begin another 6 to 9 month journey back to Earth. Another half year in space, another period of isolation and confinement, another long stretch of hoping nothing breaks. The total mission duration would be about 3 years. 36 months from leaving Earth orbit to splashing down in the Pacific or landing in a desert somewhere. 3 years of their lives spent on this one mission. And when they return, if they return, they face months of rehabilitation. Their bones are weakened. Their muscles are atrophied. Their cardiovascular systems have adapted to lower gravity and need to readjust to Earth's 1G. They'll likely need physical therapy, possibly surgery to repair damage, definitely ongoing medical monitoring for the rest of their lives to watch for radiation-induced cancers. The first Mars crew would be medical patients as much as heroes, subjects of long-term health studies, living proof of what multi-year deep space missions do to the human body. Is it worth it? That's ultimately a question of values. What is it worth to land a handful of people on Mars, let them stay for 2 years, and bring them back? What scientific knowledge would we gain that couldn't be obtained by robots? What symbolic value is there in planting a flag and leaving footprints? What inspiration might it provide to future generations? The scientific argument is weak. Robots can do most of what humans can do on Mars, and they do it without needing life support, without needing to come back, without putting lives at risk. A rover like Perseverance or Curiosity can operate for years, analyzing rocks, drilling cores, searching for signs of ancient life. It doesn't get tired, doesn't need food or water, doesn't mind the radiation. You can send 10 robots for the cost of one human mission, and if a robot fails, it's unfortunate, but not tragic. No one dies. You send another one. Humans do have advantages. Flexibility, adaptability, the ability to make complex decisions in real time, the capacity for creative problem-solving that no robot can match. A geologist on Mars could identify interesting formations, decide on the spot to investigate further, adjust sampling strategies based on what they find. A robot requires detailed instructions sent from Earth, and by the time those instructions arrive and are executed, conditions might have changed. Humans can also perform complex repairs that would be impossible for robots with current technology. But are those advantages worth hundreds of billions of dollars and significant risk of crew death? The debate continues. Some argue that exploration is what humans do, that the urge to push boundaries is fundamental to our nature, that we should go to Mars for the same reason we climbed Everest or sailed to Antarctica. Because it's there. Because we can. Because not going feels like giving up on something essential to the human spirit. Others argue that's romanticism, not rational policy. That space budgets are limited. That money spent on human Mars missions could fund dozens of robotic missions to Mars, the moons of Jupiter and Saturn, asteroids, comets, telescopes searching for Earth like planets around other stars. That the scientific return per dollar is higher for robots than for humans. That we should be driven by data, not emotions. That flags and footprints aren't worth risking lives and spending vast sums that could be used to solve problems here on Earth. What if they don't come back? A one-way mission to Mars, changes the entire equation. Suddenly, you don't need the ascent vehicle. You don't need the fuel production plant. You don't need to wait 2 years for the launch window. You don't need to provision for a 6 to 9 month return journey. The mission becomes simpler, cheaper, and ironically, safer in some ways. You send the crew, you land them, you set them up with a permanent habitat, and they live there. They become the first Martian colonists, establishing a permanent human presence on another world. But let's think carefully about what one way actually means. It's not just a technical change to the mission architecture. It's a fundamental shift in what you're asking people to do. You're not asking them to take a 3-year trip to Mars and back. You're asking them to leave Earth forever. To accept that they will never again walk on a beach, never swim in an ocean, never hike through a forest, never feel rain, never smell flowers, never attend a family gathering, never visit the place they grew up. Every goodbye is final. Every last look at Earth from their spacecraft window is really the last. There's no changed minds, no second chances, no coming home for emergencies. This isn't a new idea. Mars One, a private organization founded by Bas Lansdorp in the Netherlands, proposed exactly this in 2012. They planned to send volunteers on a one-way trip to Mars, establishing a permanent colony that would be resupplied periodically but would never bring anyone back to Earth. The plan was ambitious, perhaps overly so. They'd fund the mission through reality television, broadcasting the selection process, the training, the journey, the landing, all as entertainment. Hundreds of millions of viewers worldwide would watch as ordinary people became Martians, generating advertising revenue that would pay for subsequent missions. The response was overwhelming. Mars One received over 200,000 applications from people in over 140 countries. Teachers, engineers, students, military veterans, doctors, artists, people from every conceivable background and age group. Some were scientists with PhDs, qualified on paper for such a mission. Others had no relevant qualifications at all, but were willing to learn. What they shared was a willingness to leave everything behind for a chance to be part of this historic endeavor. The project ultimately failed. Financial problems mounted. Technical challenges proved more difficult than anticipated. Questions arose about whether the organization had the expertise and resources to actually pull off such a complex mission. By 2019, Mars One had declared bankruptcy. The company had raised nowhere near the billions of dollars needed. They'd produced promotional materials and media coverage, but hadn't built any hardware, hadn't secured launch contracts, hadn't developed the technologies necessary for keeping humans alive on Mars indefinitely. But the fact that 200,000 people applied tells us something important about human nature. People are willing to take enormous risks, make incredible sacrifices for causes they believe in, for a chance to be part of something historic, for an opportunity to matter in a way that transcends ordinary life. The psychological screening would be rigorous. The training would take years. The risks would be clearly communicated. Applicants would be told explicitly that they're choosing to spend the rest of their lives on Mars, that there's no rescue, no evacuation, no changing their minds once they launch. And yet thousands of qualified people would still apply. Throughout history, people have made similar choices. The Pilgrims, who crossed the Atlantic on the Mayflower in 1620, knew they were probably never returning to England. The mortality rate was horrific, yet people continued to come, drawn by religious freedom, economic opportunity, or simply the desire for a fresh start. The pioneers who traveled the Oregon Trail in the 1800s undertook journeys lasting months through hostile territory, leaving behind everything familiar. Many didn't survive. Ernest Shackleton's advertisement for his Antarctic expedition in 1914 read, "Men wanted for hazardous journey, small wages, bitter cold, long months of complete darkness, constant danger, safe return doubtful, honor and recognition in case of success." He received over 5,000 applications for 28 positions. They knew the risks. They went anyway. The first Mars colonists would be in this tradition. They'd be pioneers, not tourists. They'd understand that they're trading their old lives for a new existence on another world. They'd know the risks. They'd accept them. They'd train for years, learning geology, engineering, medicine, piloting, agriculture, everything they might need. They'd say goodbye to family and friends in a series of emotionally devastating farewells where everyone knows this is permanent. They'd board the spacecraft knowing they're leaving Earth forever. The psychological preparation would be crucial. You can't just select for technical skills. You need people who can handle extreme isolation, confinement, stress, and the knowledge that they're on their own. Psychiatric evaluation would identify candidates prone to depression, anxiety, or other mental health issues that could become debilitating in the Martian environment. You'd look for emotional stability, stress, resilience, the ability to function when frightened or exhausted. Interpersonal skills that allow someone to resolve conflicts constructively rather than letting them fester. Group dynamics would be carefully considered. 6 to 8 people living together for years need to be compatible. They need to respect each other, work together, support each other. One toxic personality could poison the entire crew. Studies of Antarctic research stations, submarines, and the International Space Station show that interpersonal conflict is one of the biggest challenges in isolated environments. Small irritants become major issues over time. The way someone chews food, their personal hygiene habits, their work style, their sense of humor, all of these can become sources of friction when you can't get away. The crew would need shared purpose, something that binds them together and gives meaning to their sacrifice. This is one reason why early colonists often had strong religious beliefs or ideological commitments. Their faith provided a framework for understanding hardship as meaningful rather than pointless. Modern Mars colonists might not be religious, but they'd need something similar. A deep commitment to the importance of establishing human presence on Mars. A belief that they're contributing to humanity's long-term survival. A sense that their sacrifice enables future generations to thrive on multiple worlds. Training would take years, possibly 5 to 10 years, depending on the candidates' backgrounds. They'd need to master an enormous range of skills. Basic medical procedures from setting broken bones to performing surgery. Engineering knowledge sufficient to repair or improvise fixes for almost any system in the habitat. Agricultural skills for growing food in Martian greenhouses. Geological knowledge for identifying interesting samples and conducting field research. Piloting abilities for operating rovers and drones. Construction techniques for expanding the habitat using local materials. They'd train in Mars, analog environments, remote locations on Earth that mimic some aspects of Mars. The Mars Desert Research Station in Utah, the Flashline Mars Arctic Research Station in the Canadian Arctic, volcanic regions in Iceland, high-altitude deserts in Chile. They'd spend months at a time in these locations, living in simulated habitats, going outside only in simulated spacesuits, eating simulated Mars food, dealing with simulated equipment failures. This would give them a taste of what life on Mars might be like. Though, of course, no Earth location truly replicates the combination of thin atmosphere, low gravity, extreme cold, and radiation that defines Mars. Psychological support would continue throughout training and after landing. Regular counseling sessions, group therapy, monitoring for signs of mental health deterioration. On Mars, they'd have access to telecounseling with therapists on Earth, though the communication delay limits its effectiveness. You can't have a real-time therapy session when each exchange takes 20 to 40 minutes round trip. Instead, you send updates, the therapist reviews them, and responds with advice and perspective. You watch their response hours later. It's better than nothing, but it's not the same as in-person support. The mission would likely start small, 4 to 6 people in the first crew. Their habitat would be pre-positioned, landed on Mars, months or years before they arrive, and tested thoroughly. Automated systems would deploy solar panels, establish airlocks, verify that life support is functioning. The crew's spacecraft would land nearby, close enough to walk to the habitat in an hour or two, wearing spacesuits, but not so close that landing debris could damage existing infrastructure. Their first weeks would be critical. Unload equipment from their spacecraft, move it into the habitat, set up redundant systems, test everything multiple times, establish routines for daily life, for maintenance schedules, for scientific work, begin the psychological adjustment to their new reality. The novelty would carry them through the initial period. Everything is new and exciting. They're on Mars. They're making history. They're the first humans to live on another planet. But after a few months, reality sets in. This is life now. The same habitat every day. The same few rooms. The same faces. The same food. The same routine. Mars doesn't change. The landscape looks the same today as it did yesterday, and will look the same tomorrow. The sky is always that butterscotch pink. The sun is always small and distant. The rocks are always rust-colored. There are no seasons in the way Earth has seasons, just gradual shifts in temperature as Mars orbits the sun. They'd have work to keep them busy. Scientific research is the primary justification for human presence on Mars. They'd conduct geological surveys, collect samples, search for signs of ancient life, study Martian meteorology, test technologies for future colonists. They'd set up instruments, maintain equipment, document their findings, and send data back to Earth. Scientists on Earth would analyze the results, send back questions and requests for follow-up experiments, collaborate despite the distance. Agriculture would consume significant time and attention. Growing food on Mars is essential for long-term self-sufficiency. Greenhouses would be pressurized with a mixture of nitrogen and oxygen, heated to comfortable temperatures, lit with LEDs tuned to wavelengths, optimal for photosynthesis. The colonists would grow fast-growing crops like lettuce, spinach, radishes, tomatoes, perhaps potatoes, which can provide substantial calories and grow in relatively poor soil. Rice or wheat, if greenhouse space allows. Though grains take longer and yield less per square meter than vegetables. The soil would be Martian regolith, processed to remove toxic perchlorates and supplemented with organic matter from human waste. Composting toilets would recycle biological material, though the process would need careful management to avoid pathogens. Water would come from melted ice, purified and recycled through the life support system. Nutrients would come from stockpiles brought from Earth initially, but eventually the colony would need to become fully self-sufficient, deriving everything from Martian resources. Crop failures would be devastating. If a disease wipes out the greenhouse, if a seal fails and the crops freeze, if lighting systems malfunction and plants don't get enough light, the colony faces potential starvation. They'd have emergency food supplies, freeze-dried rations, and preserved goods sent from Earth, but those are finite. If multiple crop cycles fail, they'd have to ration food severely, waiting for the next resupply mission from Earth and hoping it arrives before their supplies run out completely. Maintenance would be constant. Spacesuits develop leaks and tears. Air recyclers clog with dust. Water purifiers accumulate mineral deposits. Solar panels accumulate dust and need cleaning. Batteries degrade over time. Every system has a finite lifespan and eventually fails. The colonists would need workshops with tools, spare parts, raw materials for fabricating replacements. They'd need the knowledge and ingenuity to keep everything running far longer than it was designed to last. This is where human presence provides value that robots can't match. A human engineer can look at a broken pump, understand what failed, and figure out a workaround using available materials. They can repurpose parts from one system to repair another. They can improvise solutions that would never occur to anyone designing the equipment on Earth. The Apollo 13 crew saved themselves through exactly this kind of improvisation. Mars colonists would need the same skills, but sustained over years rather than days. Social structure would evolve organically. In a crew of 6, there's no room for rigid hierarchy. Everyone needs to contribute. Everyone's skills are valuable. Everyone's voice matters. Decision-making would probably be consensus-based, with the crew discussing issues and reaching agreement rather than having a commander issue orders. Of course, in emergencies, someone needs to make quick decisions, so they'd likely designate a mission commander with authority in crisis situations. But for day-to-day operations, collaborative decision-making builds buy-in and maintains morale. Celebrations and rituals would become important for marking time and maintaining psychological health. Birthdays, anniversaries of their landing on Mars, holidays from their various cultures. They might invent new Martian holidays, commemorating significant events in the colony's history. The first successful greenhouse harvest. The first child born on Mars, if the colony grows large enough. The first time a colonist sets foot in a new region. Conflict would be inevitable. Put 6 people together in a confined space for years, and they will get on each other's nerves. Disagreements about how to prioritize tasks, about who's doing their fair share of work, about resource allocation, about scientific versus survival priorities. Small resentments fester when you can't get away. Someone who doesn't clean up after themselves in the communal kitchen. Someone who makes too much noise during sleep periods. Someone who monopolizes communication time with Earth when bandwidth is limited. The crew would need conflict resolution skills, the ability to address issues directly but respectfully, to express frustration without attacking personalities, to forgive minor infractions rather than holding grudges, to compromise when perfect agreement is impossible. They'd probably have regular group meetings where everyone can air grievances and work through problems before they escalate. Physical intimacy is a complex issue. Will romantic relationships form? Almost certainly. If the crew is mixed gender, you can't suppress human attraction through training or selection. People will form emotional bonds, including romantic ones. The question is how to handle this without creating jealousy favoritism, or relationship drama that poisons group dynamics. Some mission planners have suggested sending couples, people already in committed relationships who've been together for years. Others argue that relationships on Earth often don't survive the stress of a Mars mission, and a breakup in a confined habitat could be catastrophic for morale. Pregnancy would be a disaster for the first missions. Not because children on Mars are inherently bad, but because the first colonists aren't prepared for childbirth and child-rearing. They don't have obstetricians, pediatricians, neonatal intensive care units. Pregnancy in low gravity with high radiation exposure carries unknown risks. Development might be different. Birth might be complicated by factors that are trivial on Earth but problematic on Mars. And even if the birth goes well, caring for an infant in a pressurized habitat, while also conducting research and maintaining life support systems, would stretch the crew beyond their capacity. Later missions, once the colony is established and larger, might include families. Children would grow up on Mars, knowing it as home. They'd learn Earth only through images and stories. They'd look at Earth in the night sky, bright enough to cast shadows when it's at closest approach, and try to imagine oceans and forests and billions of people. But it would be abstract. Mars would be real. The rust-colored dirt, the thin, cold air, the daily routines of life in a pressurized dome. Those children might never be able to visit Earth. Born and raised in 38% gravity, their bones and muscles would develop differently. Moving to Earth's 1G might be physiologically impossible. They'd feel 3 times heavier, unable to stand or walk, their hearts struggling to pump blood against the increased gravity. They'd be Martians in every sense, adapted to their world, unable to survive on the planet where their species evolved. But they wouldn't care. Earth would be the alien world. Mars would be normal. They'd grow up learning Martian geology, Martian geography, Martian history. The story of the first colonists who came from Earth and stayed. The early struggles to establish the first permanent habitats. The gradual expansion as more missions arrived. The slow development of Martian culture, distinct from Earth culture, but drawing from it. Culture would evolve in unexpected ways. Language might change. New words for Martian phenomena that have no Earth equivalent. Slang that develops from the colonist experience. Possibly even grammatical shifts over generations as Martian children learn language from parents who are using Earth languages in novel contexts. Art would reflect the Martian environment. Paintings and photographs of rust deserts and pink skies. Music composed in the strange acoustic environment of a thin atmosphere. Literature exploring themes of isolation, sacrifice, and building something new. Political structure would eventually be necessary. The first crew operates under authority from whatever organization sent them, NASA or SpaceX or a coalition of space agencies. But as the colony grows, as second and third generation Martians are born, questions of governance become unavoidable. Who makes decisions? Who enforces rules? How are disputes resolved? Do colonists have rights? Do they owe allegiance to Earth governments? Or are they autonomous? These questions might seem premature, but history shows that colonies eventually seek independence. The American colonies declared independence from Britain. Australia evolved from penal colony to independent nation. Even Antarctica, governed by international treaty, has ongoing debates about sovereignty and resource rights. Mars would follow a similar trajectory, but accelerated because the physical separation is so much greater. Earth can't send military forces to Mars. The journey takes too long, costs too much, requires too much cooperation. By the time a punitive expedition arrived, the political situation would have changed completely. A Martian declaration of independence might come decades or centuries after the first landing. Or it might come almost immediately if the first colonists feel Earth is making unreasonable demands or treating them as expendable assets rather than autonomous human beings. Imagine a scenario where Earth Mission Control orders the colonists to risk their lives for a scientific objective that seems pointless to people actually living on Mars. Do they obey, accepting Earth's authority, or do they refuse, asserting their right to make decisions about their own safety? The communication delay gives Mars an advantage in any conflict. Earth can issue orders, but Mars has 20 to 40 minutes before they even know Earth's response to their actions. By the time messages go back and forth, situations can change dramatically. Mars can present Earth with fates accomplis, actions that are already completed before Earth can object. This communication asymmetry fundamentally shifts power dynamics. Authority becomes harder to enforce when commands arrive minutes or hours after they're needed. Economic relationships would be complex. The first missions are funded by Earth governments or private organizations expecting some return on investment. That return might be scientific data, media rights, prestige, or strategic positioning for future resource exploitation. But what happens when Mars becomes self-sufficient? When colonists produce their own food, manufacture their own tools, no longer depend on Earth for survival. The economic justification for continued funding becomes murkier. Mars has resources Earth might want: water ice in vast quantities, minerals, including potentially rare earth elements, deuterium, a hydrogen isotope useful for fusion reactors if fusion power becomes viable, carbon dioxide for manufacturing, iron oxide, the rust that makes Mars red, could be processed for iron and oxygen. But extracting these resources and shipping them to Earth requires enormous infrastructure and energy. It's almost certainly cheaper to obtain the same materials from asteroids or the Moon, which are closer and have lower gravity, making launches easier. The real value Mars offers might be strategic rather than economic. A second location for human civilization, insurance against Earth-focused catastrophes. A base for exploring the outer solar system, closer to the asteroid belt and the moons of Jupiter and Saturn than Earth is. A research station for studying planetary formation, astrobiology, and long-term effects of low gravity and high radiation on humans. None of these generate profit in traditional sense, but they provide value that justifies continued investment. Over time, the colony would become more self-sufficient, relying less on Earth for basic survival needs. Each cargo mission from Earth delivers equipment that enables greater independence. 3D printers that can fabricate tools and spare parts. Industrial equipment for processing Martian ores into pure metals. Chemical plants for manufacturing plastics, fertilizers, pharmaceuticals. Genetic libraries for agricultural diversity. Educational materials for teaching Martian-born children. Each increment of independence makes the colony more resilient, less vulnerable to supply disruptions. Eventually, perhaps a century or two after the first landing, Mars might have tens of thousands of inhabitants. Cities built underground or in pressurized domes. Farms producing most of their food. Factories manufacturing most of their equipment. Universities researching Martian-specific challenges. Spaceports launching missions to the asteroid belt and the outer planets. At that point, Mars would be truly independent, a second branch of human civilization pursuing its own destiny while maintaining cultural and information connections to Earth. Think about the mass savings. A spacecraft designed for a one-way trip doesn't need to carry fuel for the return journey. It doesn't need to carry the ascent vehicle. It doesn't need as much life support capacity for those extra months in space. All of that mass can be redirected to other purposes. More supplies for the surface stay, more equipment for the habitat, more redundancy in critical systems, more scientific instruments, more of everything that helps the crew survive and thrive on Mars. The cost drops dramatically. Instead of hundreds of billions or $1 trillion, a one-way mission might cost tens of billions. Still expensive, still a major undertaking, but within the realm of what a single wealthy nation or a coalition of nations could afford. You could potentially launch a one-way Mars mission within the next 10 to 20 years with existing technology and some focused development. It wouldn't require revolutionary breakthroughs. It would just require commitment and funding. But would anyone actually go? Would people volunteer for a one-way trip to Mars, knowing they'll never see Earth again, never breathe unfiltered air again, never feel rain on their face, or swim in an ocean, or walk through a forest? Would they accept a life confined to a few pressurized habitats and spacesuits, living on a cold, dead world with a toxic atmosphere, completely dependent on technology for every breath, every drop of water, every calorie of food? The answer is yes. People would absolutely volunteer. When Mars One announced their mission, they received over 200,000 applications from people in over 140 countries. 200,000 people willing to leave Earth forever for a chance to be part of history, to set foot on another planet, to be among the first Martians. The psychological screening would be rigorous. The training would take years. The risks would be clearly communicated. And yet, thousands of qualified people would still apply. Why? Because exploration is part of human nature. Because some people value discovery more than comfort. Because the chance to be part of something larger than yourself, to contribute to humanity's future, to be remembered for generations, appeals to certain personalities in ways that safety and familiarity never could. The people who crossed the Atlantic to colonize the Americas in the 1600s knew they were probably never coming back. The journey was dangerous. The destination was unknown. The life would be hard. Many didn't survive. But they went anyway, driven by hope, by ambition, by the desire for something new. The first Mars colonists would be similar. They'd be pioneers, not tourists. They'd understand that they're trading their old lives for a new existence on another world. They'd know the risks. They'd accept them. They'd train for years, say goodbye to family and friends, and board the spacecraft knowing they're leaving Earth forever. And here's the thing, once they're on Mars, they wouldn't need rescue. They'd need supplies, yes. Regular cargo missions from Earth, delivering food, spare parts, medical supplies, new equipment. But they wouldn't need to be evacuated. They'd adapt. They'd make Mars their home. They'd learn to live in that environment, to work in that environment, to thrive in that environment. Over time, the colony would become more self-sufficient, growing more of its own food, manufacturing more of its own tools, relying less and less on Earth for basic survival. Eventually, years or decades down the line, the Mars colony might develop the capability to manufacture a return vehicle. They'd have the industrial base, the fuel production, the expertise. Someone born on Mars, someone who'd never seen Earth except as a bright star in the sky, might decide they want to visit the homeworld of their species. And at that point, the technology and resources would exist to make it possible. But that would come later, after the colony is established, after the infrastructure is built, after Mars has become a second home for humanity. The first humans to Mars almost certainly won't come back, because bringing them back isn't the goal. The goal is to establish a permanent human presence on another world, to ensure that humanity isn't confined to a single planet, vulnerable to whatever disasters might befall Earth. An asteroid impact, a supervolcano, a pandemic, nuclear war, climate catastrophe. Any of these could devastate Earth's ecosystem and threaten human civilization. But if there are people on Mars, if there are self-sustaining colonies on multiple worlds, then humanity as a species survives. We become an interplanetary civilization, spreading across the solar system, no longer betting everything on one planet. This is the real reason for going to Mars and staying there. Not because it's easy or cheap or safe, but because it's necessary for our long-term survival, because putting all of humanity's eggs in one basket, even a basket as beautiful and life-supporting as Earth, is a risk we shouldn't accept if we have the technology to do something about it. Mars is the obvious first choice for a colony. It's the closest planet with a solid surface that isn't a hellish inferno like Venus. It has water ice that can be extracted and purified. It has an atmosphere, thin as it is, that can be processed for oxygen and nitrogen. It has a day length, 24 hours and 39 minutes. That's close enough to Earth's day that humans can adapt without too much difficulty. It has seasons caused by its axial tilt, though they're about twice as long as Earth's seasons, because Mars takes longer to orbit the Sun. It has temperatures that, while cold by Earth standards, are survivable with proper insulation and heating. The average temperature is minus 63 degrees Celsius, but near the equator in summer, temperatures can reach a comfortable 20 degrees Celsius during the day, before plunging to minus 73 degrees Celsius at night. The low gravity is a challenge. At 38% of Earth's gravity, long-term residents would experience bone density loss and muscle atrophy. Children born on Mars might develop differently than children on Earth, with weaker bones and muscles adapted to lower gravity. They might never be able to visit Earth because they couldn't withstand the higher gravity. But they also wouldn't care. Mars would be their home. Earth would be the alien world, the place with crushingly heavy gravity, where everything weighs nearly 3 times as much. The radiation is a serious concern. Mars has no magnetic field and a thin atmosphere, so cosmic rays and solar radiation reach the surface with minimal shielding. Long-term exposure increases cancer risk and could cause other health problems. The colonists would need to build habitats with radiation shielding, possibly underground or covered with Martian regolith. They'd need to limit their time outside in spacesuits. They'd need medical monitoring and treatments for radiation exposure. But these are solvable problems. We know how to shield against radiation. We know how to monitor exposure levels. It's an engineering challenge, not an impossible barrier. The psychological challenges might be harder to solve than the physical ones. Humans evolved for life on Earth, for blue skies and green plants, and the sounds of wind and water and wildlife. Mars has none of that. The sky is butterscotch pink during the day, fading to blue near the sun during sunset, in a reversal of Earth's colors. There are no plants except what you grow in greenhouses. No animals, no insects, no birds, no sounds except what humans and their machines make. The landscape is beautiful in its own stark way. Vast rust-colored deserts, towering volcanoes, deep canyons that dwarf anything on Earth. But it's empty, lifeless, alien. The colonists would need to create their own culture, their own society, their own reasons for being that go beyond mere survival. They'd need art and music and literature. They'd need games and celebrations and rituals. They'd need connection to each other and to their mission. They'd need to build a community that can sustain itself psychologically as well as physically. This might be the hardest part of the entire endeavor. Not the technology, not the logistics, but the human element. Keeping people sane and motivated and engaged over years and decades in an environment that's fundamentally hostile to human life. But here's what gives me hope. Humans are adaptable. We've colonized every environment on Earth, from the Arctic to the Sahara, from high mountain valleys to tropical islands. We've lived on the International Space Station continuously since the year 2000, maintaining a human presence in space for over 2 decades. We've learned how to thrive in places that would kill us without our technology. Mars would be the ultimate test of that adaptability, but it's not beyond our capabilities. The first Mars colonists would be heroes. They'd be remembered for as long as human civilization exists. Their names would be taught to children on both Earth and Mars. They'd be the Neil Armstrong and Buzz Aldrin of the next generation, the people who took the first steps toward making humanity a multiplanetary species. But unlike Armstrong and Aldrin, who spent a few hours on the moon and came home, the Mars colonists would live there. They'd live out their lives there. They'd be buried in Martian soil, their remains becoming part of another world. And that's beautiful in its own way. Humans evolved on Earth, but we're capable of becoming something more. We're capable of adapting to new worlds, of making homes in places where no human has ever lived. The first people to pass away on Mars would be the first humans whose atoms never return to Earth. They'd be scattered on another planet, part of Mars forever. Their sacrifice would make possible every future generation of Martians. Their decision to go and never return would open the door for millions or billions of people to follow, to build cities and farms and schools, to terraform the planet over centuries, to make Mars a true second Earth. Because that's the long-term vision, not just a small outpost of a few dozen people struggling to survive, but a thriving civilization with millions of inhabitants. Cities under domes or underground, connected by tunnels and transit systems. Farms producing food, factories manufacturing goods, universities researching new technologies, a government, a culture, an economy. A world that's distinctly Martian while still retaining connections to its Earth heritage. Getting there would take centuries. The first colonists would only see the very beginning. They'd live in small habitats, probably underground, or in lava tubes for radiation protection. They'd work constantly to maintain their life support systems, to grow food, to conduct research that justifies the massive expense of keeping them supplied from Earth. They'd know they're building a foundation for something they'll never see completed. They're planting seeds that won't bear fruit for generations. But they'd also know they're necessary. Someone has to go first. Someone has to prove it's possible. Someone has to establish that foothold, that first permanent human presence on another world. And they'd get to experience things no one in history has experienced. They'd be the first humans to watch the sun rise on Mars, small and distant compared to how it looks from Earth. They'd be the first to see the Martian moons, Phobos and Deimos, racing across the sky. They'd be the first to explore the canyons and volcanoes, to study Martian geology firsthand, to search for signs of ancient life in the rocks and ice, because Mars might have had life once. Billions of years ago, Mars was warmer and wetter. It had rivers and lakes, maybe even an ocean in its northern lowlands. It had a thicker atmosphere, a magnetic field that protected the surface from radiation, conditions that might have been suitable for life to emerge. Then, something changed. Mars lost its magnetic field, possibly due to its core cooling. Without magnetic protection, solar wind gradually stripped away the atmosphere. The water froze or evaporated into space. The planet became the cold desert we see today. But if life did exist on ancient Mars, traces might remain. Fossils preserved in sedimentary rocks, organic molecules frozen in ice, perhaps even dormant microbes in underground aquifers, if any liquid water still exists below the surface. The Mars colonists would have the opportunity to search for this evidence, to answer one of the most profound questions in science. Did life arise independently on Mars? Or is Earth the only world in the solar system that ever hosted life? Finding evidence of past life on Mars would revolutionize our understanding of biology and our place in the universe. It would prove that life can arise wherever conditions are suitable, that Earth isn't unique, that the universe might be teeming with life on billions of planets around billions of stars. It would change everything. And even if Mars never had life, studying its geology and climate would teach us about planetary evolution, about how worlds change over billions of years, about what makes a planet habitable and what causes habitability to fail. This knowledge would help us understand Earth better, help us predict how our own planet might change, help us identify potentially habitable exoplanets around other stars. The science alone would justify the mission. But the true justification is simpler. We go to Mars and stay there because we can. Because the alternative is to remain on Earth forever, never expanding, never exploring, never taking the next step in our evolution as a species. Humanity has always pushed boundaries. We've always wondered what's over the next hill, across the next ocean, on the next continent. Now, we can look at the next planet and ask the same question. What's there? What can we learn? Can we live there? The answer to that last question is yes, but it requires commitment. It requires people willing to go and never return. It requires accepting that the first Mars colonists are embarking on a one-way journey. They're leaving Earth behind, trading everything familiar for a chance to be part of the greatest adventure in human history. They won't come back. They can't come back. Not because it's technically impossible, but because the resources needed to bring them back could be better spent sending more colonists, more supplies, more equipment. Because every kilogram of fuel manufactured on Mars for a return journey is a kilogram of fuel not available for exploring Mars or for building the colony's infrastructure. Because bringing people back defeats the purpose of the mission, which is to establish a permanent presence, not to visit and leave. And the colonists would understand this. They'd accept it. They'd look back at Earth one last time as their spacecraft departs, watch it shrink to a point of light, and then turn their attention forward to Mars, to their new home, to the future. This is why the first humans on Mars will never come back. Not because of failure, not because of disaster, not because they're abandoned, but because coming back was never the plan. The plan is to stay, to build, to prove that humans can live on another world. To take the first step towards spreading humanity across the solar system and eventually beyond. It's a profound sacrifice and an incredible opportunity. Those first colonists will give up everything they knew on Earth, all the comforts and familiarities, all the connections to friends and family, all the simple pleasures of breathing fresh air and feeling rain and seeing green growing things everywhere. They'll trade all of that for a harsh existence on a cold desert planet where survival requires constant vigilance and where tragedy is always one equipment failure away. But they'll also gain something no one else has ever had. They'll be the first to live on another world, the first to call another planet home, the first to prove that humanity's future extends beyond Earth. Their names will be in history books forever. Children born centuries from now, growing up in Martian cities with millions of inhabitants, will learn about the first colonists the way we learn about the Mayflower passengers or the Lewis and Clark expedition. And those future Martians, living in a thriving civilization with terraformed regions that have breathable air and liquid water, might look back at the first colonists with a mixture of admiration and incomprehension. They might not fully grasp how hard it was, how much courage it took, how many sacrifices were made. The same way we sometimes forget how difficult life was for early colonists on Earth. The people who crossed oceans in wooden ships, who built settlements in wilderness, who survived winters without modern heating or medicine. But that's okay. The point isn't for future generations to suffer the way early pioneers suffered. The point is for the pioneers to make things easier for everyone who comes after, to establish the first habitats that later colonists can expand, to set up the first farms that teach future farmers what works on Mars, to build the first infrastructure that later engineers can improve and extend, to make the mistakes so that future Martians don't have to pay the price of being first. That's always been the role of pioneers. They go into the unknown, they face the dangers, they solve the unsolvable problems, and they make it possible for others to follow. The first colonists on Mars will do the same. They'll go knowing they're never coming back, accepting that sacrifice as the price of making history, of being part of something larger than themselves. And as their spacecraft approaches Mars, after 6 to 9 months of travel, as they prepare for that terrifying descent through the thin atmosphere, as they touch down on the surface and open the hatch for the first time, they'll step out onto rust-colored soil under a pink sky, and they'll plant the first footprint. They'll speak the first words on Martian ground. They'll look up at the small, distant sun and the unfamiliar constellations and the 2 tiny moons racing overhead, and they'll know they're home, not on Earth anymore, not ever going back. But home nonetheless. Because home isn't just where you're born. Home is where you build your life, where you contribute to something meaningful, where you belong to a community working toward a shared future. And for the first Mars colonists, that home will be a new world, harsh and unforgiving, but full of possibility. They'll build that future one day at a time. They'll expand the habitats, drill for water ice, tend the greenhouses, conduct experiments, explore the landscape, and gradually, over years and decades, they'll transform a lifeless planet into something that resembles a home. Not Earth, never Earth, but something new, something human. Something that proves we can adapt to anything, survive anywhere, thrive in conditions that should kill us. And they'll do it, knowing that behind them, millions of miles away, Earth continues spinning. Life goes on. People are born, lives end, civilizations rise and fall, and eventually, if we don't destroy ourselves, if we solve the problems that threaten our existence, more missions will launch. More colonists will make that one-way journey. The Mars population will grow from tens to hundreds to thousands to millions. And someday, maybe centuries from now, Earth and Mars will be sister worlds. Two planets hosting human civilization, two homes for a species that started on one world but refused to be confined there. Two branches of humanity, sharing a common heritage but developing along different paths, each shaped by their environment, their challenges, their triumphs. That future starts with the first colonists. The ones who go and never return. The ones who trade Earth for Mars. The ones who become, in the most literal sense possible, aliens. Humans who live on an alien world, who adapt to alien conditions, who might eventually evolve into something distinctly Martian over thousands of generations. This is the story of why the first humans on Mars will never come back. Not because they failed, not because they're trapped, but because they succeeded beyond what any previous generation of explorers accomplished. They didn't just visit a new land. They made it their land. They claimed another planet for humanity. They proved we can do this. We can leave our homeworld. We can survive on other worlds. We can become a multi-planetary and eventually a multi-stellar species. The first footprints on Mars will never be erased. There's no wind strong enough, no water to wash them away, no vegetation to overgrow them. They'll remain in the Martian dust for millions of years, a permanent testament to the moment when humanity took its first steps toward becoming something more than a single-planet species. And the people who make those footprints, who breathe filtered Martian air and drink recycled water and eat hydroponic vegetables grown under LED lights, who watch Earth set below the horizon, knowing they'll never stand on that world again. Those people are heroes in the truest sense. They're giving up everything familiar, everything comfortable, everything easy, to make possible a future most of them won't live to see. That's why they won't come back, because coming back would mean abandoning that future. And they're not the kind of people who abandon things. They're the kind of people who see something that needs to be done, something that's never been done before, something that will echo through history for as long as humans exist, and they say, yes, I'll do it, I'll go, I'll stay, I'll build something new on another world. And when those first colonists are old, when they've spent decades on Mars, when younger colonists arrive who were children, when the mission launched, or who weren't even born yet, those first pioneers will be able to look back on their lives and know they were part of something extraordinary. They won't regret the choice. They won't wish they'd stayed on Earth. They'll know they made the right decision, because they'll see what they built. Not just habitats and farms and equipment, but a civilization, a community, a home for humanity on another world. They'll see children playing in pressurized playgrounds, learning to walk in the strange low gravity that makes every step a small hop. They'll see scientists making discoveries that answer questions humans have asked for centuries. Where did Mars water go? Did life ever arise here? How do planets evolve from young hot worlds to old cold ones? What happens to human biology after generations in low gravity and high radiation? These questions will have answers because the colonists were there to find them. They'll see engineers solving problems that seemed impossible. How do you manufacture electronics without the complex supply chains that exist on Earth? How do you build habitats from local materials when those materials are nothing like what we use on Earth? How do you maintain technology in an environment that constantly tries to destroy it? The first generation will struggle with these challenges. The second generation will refine the solutions. The third generation will have answers so well established that they're just standard practice, the way things are done on Mars. They'll see artists creating works that capture the unique Martian experience in ways that Earth-bound people can never fully appreciate. Paintings that capture the precise shade of pink in the Martian sky at sunset, when the blue shifts toward purple and the dust scatters light in patterns that have no Earth equivalent. Sculptures carved from Martian rock, shaped by artists who understand how the stone breaks under low gravity. Music composed on instruments that have been modified to work in the thin, low-pressure atmosphere where sound travels differently than on Earth. Poetry written in the quiet of a Martian night when Phobos and Deimos race across the sky, and Earth is just a bright star, barely distinguishable from Venus. They'll see community forming, traditions developing, holidays celebrated, weddings held in greenhouses, surrounded by the food crops that keep everyone alive, memorial services for those who've passed, their ashes scattered on the Martian surface, becoming literally part of the planet they helped tame. Each funeral a reminder that this is permanent, that these people gave their lives, literally, for this project. They came to Mars, and they stayed until the end. And they'll know that their decision to go and never return made all of it possible. That without them, without their courage and sacrifice and willingness to leave everything behind, none of it would exist. Mars would still be an empty world, waiting for someone brave enough to make it home. They were brave enough. They went. They stayed. They built a future. The emotional weight of that knowledge would be profound. They'd understand that their names will be taught to every child on Mars for as long as human civilization exists on that planet. The way we teach children on Earth about the Wright brothers or Neil Armstrong or Marie Curie. People who fundamentally changed human possibility. Before the Wright brothers, humans couldn't fly. After them, we could. Before Armstrong, humans were confined to Earth. After him, we'd walked on another world. Before the first Mars colonists, humanity was a single-planet species. After them, we were multi-planetary. This shift in human status from single-planet to multi-planet species represents one of the most significant transitions in the history of life on Earth. For 3.8 billion years, life existed only on this one world. Every organism that ever lived, from the simplest bacteria to the most complex plants and animals, spent its entire existence within a few kilometers of Earth's surface. We're all descended from a single origin of life, all branches of one family tree, all sharing the same DNA structure, the same basic biochemistry, the same dependence on liquid water and organic carbon. Then, humans developed technology. We learned to understand the universe through mathematics and observation. We built machines that could leave Earth's surface. We sent probes to other planets, gathering data, testing hypotheses, expanding our knowledge. And eventually, we developed the capability to send ourselves, to establish permanent presence beyond our birth world. That capability changes everything. It means that a catastrophe on Earth, no matter how severe, no longer means extinction for our species. An asteroid impact, a supervolcano eruption, a pandemic, a nuclear war, runaway climate change, any of these could devastate Earth's biosphere and kill most or all humans on this planet. But if there are humans on Mars, if there are self-sustaining colonies on multiple worlds, then humanity, as a species, survives. The knowledge we've accumulated, the art we've created, the stories we've told, all of it continues. Civilization can recover, can rebuild, can eventually return to Earth if it becomes habitable again, or can spread to still more worlds if Earth remains uninhabitable. This isn't hypothetical risk management. This is accepting that Earth has been hit by extinction-level asteroids before and will be again. 66 million years ago, an asteroid about 10 kilometers in diameter struck what is now the Yucatan Peninsula. The impact released energy equivalent to billions of nuclear weapons. It threw so much dust and debris into the atmosphere that sunlight was blocked for months or years. Plants couldn't photosynthesize. Food chains collapsed. The dinosaurs, which had dominated terrestrial ecosystems for 160 million years, went extinct, along with about 75% of all species on Earth. That wasn't the only mass extinction in Earth's history. The Permian-Triassic extinction event, 252 million years ago, killed about 96% of all marine species and 70% of terrestrial vertebrate species. The cause is still debated, possibly volcanic eruptions on unprecedented scales, possibly an asteroid impact, possibly a combination of factors. Whatever the cause, Earth's biosphere came terrifyingly close to being sterilized. Life survived, barely, and evolution over tens of millions of years repopulated the planet with new species. But intelligence, consciousness, civilization, these are recent developments. Anatomically modern humans have existed for about 300,000 years. Civilization as we know it, with cities and writing and agriculture, has existed for only about 10,000 years. We're newcomers on a planet that's 4 billion years old. We don't know if consciousness is common in the universe. We don't know if intelligence inevitably arises, given enough time and the right conditions. We don't know if technological civilization is a typical outcome of evolution or a bizarre fluke that's occurred only once in the observable universe. But we do know that consciousness and intelligence and civilization exist here, now, on this planet. And we know they're fragile, vulnerable to catastrophes that care nothing for the significance of what they destroy. Becoming a multi-planet species provides insurance against that fragility. It's the civilizational equivalent of backing up critical data to multiple locations. If one location fails, the backup allows recovery. This isn't cowardice or giving up on Earth. It's wisdom. It's recognizing that sometimes the best way to preserve something precious is to not keep all of it in one place. The first Mars colonists would understand this at a visceral level. They're the backup. They're the insurance policy. Their existence on Mars means that humanity can survive catastrophes that would otherwise end us. They're living in uncomfortable conditions, sacrificing normal human experiences, exposing themselves to health risks, precisely because they understand the stakes. They're not doing it for themselves. They're doing it for the species, for the future, for the possibility that human consciousness and civilization continue even if Earth becomes uninhabitable. There's also a philosophical dimension that goes beyond mere survival. Humans have always been explorers. We originated in East Africa and spread across the entire planet, reaching every continent, adapting to every climate from Arctic tundra to tropical rainforest to high-altitude plateaus. We crossed oceans in primitive boats, navigating by stars and currents and the flight patterns of birds. We climbed the highest mountains, not because there was anything useful at the top, but because they were there, and we wanted to know what it was like to stand on the summit. This drive to explore, to push boundaries, to see what's beyond the horizon, is deeply embedded in human psychology. Some people are content to stay where they are, to live in familiar surroundings, to follow established patterns. Others feel a restlessness, a need to move, to discover, to experience new things. Both are valid ways to be human. Society needs both. We need people who maintain stability, who perfect existing systems, who build communities and raise children in safe, predictable environments. We also need people who venture into the unknown, who take risks, who report back about what's out there and whether it's safe for others to follow. The first Mars colonists would be that second type. They're the scouts, the pioneers, the people who go first so others can follow more safely. They accept higher risks because they understand someone has to, and they're willing to be that someone. This isn't recklessness or a death wish. It's courage, informed by clear-eyed assessment of danger. They know the risks. They choose to proceed anyway because they value the goal more than they fear the danger. Throughout history, we celebrate these people. We build monuments to explorers and pioneers. We tell their stories to children, holding them up as examples of human capability at its best. The first Mars colonists would deserve similar recognition, not because they went to Mars, but because they stayed, they committed, they built something permanent. They transformed an abstract human capability into concrete reality. Before them, we could talk theoretically about living on other planets. After them, we actually do it. Their decision to never return would be central to their legacy. They could have demanded a return option. They could have insisted on ascent vehicles and fuel plants and all the infrastructure needed to bring them back. But they recognized that insisting on return options would make the mission exponentially more expensive and difficult, possibly impossible with current technology and budgets. So they accepted a one-way trip. They gave up Earth forever. They made the ultimate sacrifice, not of their lives immediately, but of their ability to ever return to the world where they were born. That sacrifice enabled the mission to happen. It reduced costs, simplified logistics, allowed resources to be focused on making the Mars colony sustainable rather than on bringing people back. Every kilogram not spent on ascent vehicle fuel is a kilogram that can be spent on greenhouses, tools, scientific instruments, medical supplies, things that improve life on Mars and enable the colony to grow. And growth is essential. A colony of 4 to 6 people is a foothold, not a civilization. It's vulnerable to accidents, to equipment failures, to simple bad luck. If 2 people are lost in an accident, the colony might not have enough people left to maintain all the critical systems. But a colony of 40 people has redundancy. A colony of 400 has specialization, with doctors and engineers and farmers and teachers. A colony of 4,000 has culture, economy, political structure. It becomes self-sustaining, not just technologically, but socially and psychologically. Getting from 6 to 6,000 requires continued missions from Earth, at least in the early decades. Each mission brings more colonists, more equipment, more genetic diversity, more knowledge and skills. The growth might be exponential if each successful mission encourages more funding and more volunteers. Or it might be linear, with missions arriving every few years as budgets allow. Or it might stall if missions fail, if public support wanes, if political priorities shift. History offers examples of all 3 patterns. European colonization of the Americas started slowly with a few failed attempts, then exploded. As success became apparent, and economic opportunities attracted massive investment. Antarctic research stations grew slowly and remain small because there's limited economic incentive to support larger populations. Space station programs have shown that sustained presence in a hostile environment is possible but politically fragile, dependent on continued funding and international cooperation that can evaporate with changing governments. Mars colonization would likely follow a boom and bust pattern. Initial excitement and rapid growth as the first missions succeed and capture public imagination. Then, a plateau as the challenges become apparent and costs mount. Possibly a collapse if a major disaster kills colonists or if economic recession on Earth forces budget cuts. Then, gradual recovery as new technologies reduce costs or new motivations emerge. The overall trend would be upward, but with setbacks and difficult periods that test the commitment of everyone involved. The first colonists would experience the initial excitement, but might not live to see the full realization of the colony they founded. They'd be in their 40s or 50s when they land, after years of training and selection. They'd spend perhaps 20 to 30 years on Mars, working to build the colony, welcoming new arrivals, passing on their hard-won expertise. Then they'd age, their bodies wearing out faster than they would have on Earth, due to radiation exposure and low gravity effects. They'd reach the end of their lives on Mars, probably in their 70s or 80s, surrounded by a small but growing community. Their funerals would be community events. Everyone on Mars would attend. They'd gather in the largest, pressurized space available, share stories about the deceased, celebrate their contributions, grieve their loss. Then they'd take the body outside in a respectful procession, spacesuits moving slowly in the low gravity, and commit it to the Martian soil. No burial in the traditional sense, because permafrost makes digging difficult. More likely, the body would be placed in a designated area, covered with rocks, marked with a simple monument. The first Martian cemetery, where the founders of human civilization on Mars rest permanently. Future colonists, arriving years or decades later, would visit that cemetery as a pilgrimage site. They'd stand before the markers of the first colonists and reflect on the courage it took to come here, knowing they'd never leave. Children born on Mars would learn about these people in school, study their decisions, understand that their own existence is possible only because these pioneers accepted a one-way ticket. And somewhere, among those later arrivals, might be the grandchildren of the first colonists. Children who were small when their parents left for Mars, or weren't even born yet. They grew up on Earth, hearing stories about mom, or dad, or aunt, or uncle who went to Mars. They saw videos of the landing, messages sent back across the void, images of the red landscape, and they decided they wanted to see that world themselves, to follow their family members' path, to be part of the same grand endeavor. These second-generation Mars migrants would arrive to find a world their relative helped create. They'd walk through habitats their family member built. They'd eat food grown in greenhouses their family member designed. They'd meet people who worked alongside their family member, who could share stories and memories. And if they're lucky, if the timing worked out, they might arrive while their family member is still alive, still lucid enough to recognize them, still capable of understanding that this person from Earth came all this way for a final reunion. Imagine that meeting. An elderly colonist, body bent by decades of low gravity and radiation, mind perhaps clouded by age but still functional, seeing for the first time in 30 years someone from their old life. Their daughter, now middle-aged herself, who made the 6 to 9 month journey to Mars, knowing her parent might not survive until she arrived. They'd embrace, as well as spacesuits allow, or if they're inside the habitat, properly, without the encumbrance of suits. They'd talk for hours, days, exchanging life stories, bridging decades of separation. The colonist would share what they've learned about Mars, about building something new, about the satisfaction of seeing a dream become reality. The daughter would share news from Earth, updates about family and friends, changes in technology and culture that the colonist has only heard about through messages and reports. And then, eventually, the elderly colonist would reach the end. But in their final days, they'd know their family came, that the connection wasn't completely severed. That love can bridge the distance between planets, even if it takes 30 years to complete the journey. They'd spend their final days on Mars, the planet they chose, surrounded by the community they helped create, with family present for the end. Not a bad way to go, all things considered. Better than many people get on Earth. These stories would become part of Martian culture, the family that spans 2 planets, the pioneer who never returned to Earth but whose children came to Mars, the sacrifice and the reunion, the permanent separation and the unexpected connection. These narratives would help future Martians understand their history, their relationship to Earth, the choices that brought them into existence. Because everyone on Mars is there because someone made a choice. Either they chose to come themselves or their parents chose to come, bringing them as children or conceiving them after arrival. No one on Mars is there by default. No one was born into Martian life without some act of will in their history. This would create a culture fundamentally different from Earth, where most people live in the country they were born in, following patterns established by circumstance rather than choice. Martians would grow up understanding that their existence required someone's active decision, that humans aren't on Mars by accident or evolutionary inevitability, but because specific people made specific choices to go and stay and build. This awareness might foster a culture that values intentionality, that sees life as something you actively create rather than something that happens to you. Or it might create pressure to justify one's existence, to prove that you're worthy of the sacrifices your ancestors made. Or it might produce a combination of both, a culture that's simultaneously empowered and burdened by the weight of its own history. Earth cultures developed over thousands of years, shaped by geography, climate, available resources, migrations, conquests, trade, technological change, and countless other factors. Martian culture would develop much faster, condensed into decades or centuries, and shaped primarily by the constraints of living on a hostile planet and the shared experience of being pioneers. The first colonists would set the tone, establish initial norms, create the founding myths. Later, arrivals would modify and add to that foundation. Children born on Mars would absorb it and make it their own, changing it further. Within a few generations, Martian culture would diverge significantly from Earth culture. Language would change, developing Martian-specific vocabulary and possibly new grammatical structures. Social norms would adapt to the realities of life in confined spaces with limited resources. Values would shift to emphasize cooperation, sustainability, long-term thinking, because individual survival depends utterly on community survival. The artistic and intellectual traditions would reflect the Martian experience, creating works that Earth audiences might find alien or incomprehensible, even though both societies share common ancestry. And the first colonists, those who made the one-way trip, would be mythologized. Their real struggles and failures and human flaws would be smoothed over, replaced with idealized versions that serve the needs of later societies. They'd become cultural heroes, larger-than-life figures who embody virtues that Martian society wants to promote. The truth of who they actually were, ordinary humans with extraordinary courage who made an irreversible choice and lived with the consequences, might get lost in the legend. But that's how cultures work. We tell stories about our origins that serve our present needs. The stories don't have to be perfectly accurate to be meaningful. What matters is that they convey important truths, that they help people understand where they come from and why they exist. The first Mars colonists, by choosing to never return, gave future Martians a powerful origin story. The pioneers who left Earth forever to build a new world, who sacrificed everything familiar for an idea that something better could be created elsewhere, who bet their lives that humans could thrive on Mars and prove themselves right. That story would inspire generations. It would be told to children learning their history, referenced in political speeches when leaders need to evoke shared purpose, remembered in quiet moments when someone faces a difficult choice and needs courage. The story of the first colonists who didn't come back because they never intended to, because coming back was never the plan. The plan was to stay, to build, to transform Mars from an empty world into a home. And in executing that plan, in living that story, they would do something no other humans have ever done. They'd prove that our species can persist beyond our birth world, that we're capable of adapting to conditions radically different from what we evolved for. That human consciousness and civilization are not confined to Earth, but can spread, can take root in new places, can establish themselves permanently on multiple worlds. That's not just exploration. That's not just adventure. That's existential insurance for the species. That's taking evolution into our own hands and directing it towards survival across cosmic timescales. That's ensuring that whatever happens to Earth, whether catastrophe or gradual decline, or simply the natural evolution of our star toward red giant phase billions of years from now, humanity continues somewhere. Our ideas, our art, our knowledge, our consciousness, all the things that make us human, persist and grow and change and eventually become something we can't predict or imagine. Thank you for joining me on this exploration of why the first Mars colonists will embark on a one-way journey. If you found this thought-provoking, a like or subscribe would help this channel continue examining the profound questions about humanity's future in space. These deep dives into what space exploration really means take considerable thought and research to create properly. The journey to Mars represents more than just technological achievement. It represents a fundamental shift in how we think about ourselves as a species. We're no longer bound to one world. We have the knowledge and the capability to spread across the solar system. Whether we choose to do so, whether we commit the resources and accept the sacrifices, remains to be seen. But if we do, if those first missions launch and those first colonists land and stay and build, they'll be doing something no generation before them could do. They'll be making humanity a multi-planet species. They'll be ensuring our long-term survival. They'll be opening a frontier that could keep us exploring and discovering and growing for thousands or millions of years. And it all starts with people willing to go on a one-way trip, willing to leave Earth forever for a chance to be part of that future. That's not just exploration. That's transformation. That's evolution. That's humanity taking the next step. And those first footprints on Mars the ones that will never fade, will mark the moment when we took that step, when we proved we could, when we chose to reach for something greater than ourselves. That's why they won't come back. Because they're building something that will last far longer than any individual life. Something that will outlive nations and civilizations. Something that will endure as long as humans exist anywhere in the universe. They won't come back because they're going home, to a new home, to Mars. And that's exactly where they'll stay.